So before beginning these flooding experiments, what we wanted to do is start by taking a look at some of what we wanted to answer. And we wanted to begin by looking at the resurfacing processes that were potentially occurring in early planetary history. So you have the impact crater and basin ejected deposits as well as volcanism. And we really wanted to focus on the volcanic resurfacing. And so look at these different deposits and try to understand how they, what changes when you have different cratering rates, when they're much higher, such as on the Moon and Mercury, and also specifically when there's an albedo contrast, when it's particularly low, as on Mercury. In addition, getting a better constraint on the thicknesses of volcanic fill and volcanic plains is really important to understand volumes and fluxes of material that are being emplaced onto these planetary surfaces. And in addition to that, we wanted to begin to employ the crater size frequency distributions and see how much information we'd be able to extract from those on these particular surfaces. So volcanic plains occur on all terrestrial planets. We have flood basalts that can reach volumes as high as 10 to the 6 kilometers cubed, and some of these individual flows can be as long as 750 kilometers. In addition, they occur as episodic eruptions, and you can see that here in this lovely picture of the Deccan traps with the horizontal layering occurring here. I also have images of Mars, Mercury, and flows in Imbrium Basin on the Moon as well. So some previous work has been done. In 1982, had begun to look at older topography and flooding of Oriental Basin and also the edges of the Imbrium Basin in order to get an understanding of the geometry, sequence of fill, and actual fill volumes of lunar basins. And this again goes back to understanding the flux of material that's been emplaced on the surface. And some interesting results that they came up with is that there are 2 stages of basin filling. You have an initial stage where there are very thick deposits that have a small area. Sorry about that. Which is shown in this graph right here, and then the later stages of filling involve much thinner deposits that are much more areally extensive, which you can see is displayed here in this graph. So we began by flooding various lunar terrains. We used the LOLA data and used the 128 pixel per degree data set. All have 3 study regions, and they're all 600 by 600 kilometers. And I flooded each of these regions in half-kilometer increments and began with the assumption that the flooding starts at the very lowest elevation and continues simultaneously throughout the study region with each increment. And in addition to this, while I was doing the flooding, I kept track of the crater size frequency distribution and how it evolved with the flooding. So initially, we mapped all craters in these 3 regions greater than 5 kilometers in diameter. And those included in each of the regions were included if the majority of their area, their centers, were contained within the predefined areas. We used the crater stats program. And then another assumption that we made was that these craters were disappearing from the crater size frequency distribution once their entire rim had been buried, which, if you're working in the opposite direction on this problem in a planetary surface, you might not consider some of these remaining craters to actually be there because you're seeing a knob or something that's just sticking up through the Mare material. Here's a map showing the 3 study locations that we concentrated on. The very first area is over here on the far side, and it's some of the most heavily cratered terrain on the Moon, as found out by Head et al. In 2010, where they looked at craters that were greater than 20 kilometers in diameter. The next area we looked at was an older basin, the Hertzsprung Basin. And lastly, this area on the near side, the Central Highlands, located just to the west of Nectaris Basin. The first area is the heavily cratered terrain. It's got a relief of just under 10 kilometers total. So here's an image showing my entire study area for here, 600 by 600 kilometers. And over here on your right, I'm showing you a graph of the elevation and volume change. And what you can see here is initially you have this stage where there's not much increase in volume, but then you reach a certain point where the volume increases by a factor of 34. So I'm going to show you an animation of this. Yeah, okay. And so you'll see that there's a shoulder that forms, and it forms once you see intercrater style plains start to develop. These individual craters will fill, and you'll start to get material in between those, and that's when you actually start to see this large jump and the volume of material in this area. So in addition to that, I took a look at the crater size frequency distribution, and here is the initial cumulative crater frequency, and we have diameter over here on your x-axis. And what you'll see in the next slide when I animate this is a lot of the smaller craters will disappear, and then it'll hit a certain point where all of a sudden craters will start to become erased or disappear at much faster rates. And that point occurs right as these intercrater style plains start to develop. Okay, so you see not much occurring now, but right about now you start to see a significant decrease in the crater population here, and then eventually the loss of small craters kind of propagates down and you begin to lose larger craters as well. The second area I took a look at was Hertzsprung Basin. This particular area has the largest amount of total relief. It's 10.7 kilometers here. Again, I have a similar elevation versus volume graph, and I'll begin the animation here. And this is a little bit different from the previous area in that once this inner ring is breached, you begin to see this sudden increase in the amount or volume of material that is being emplaced. And so what's really interesting in comparison to the crater size frequency distribution of the heavily cratered terrain is that it's got some unique features that occur due to the topography. Right here in craters that are approximately 30 to 60 kilometers in diameter, you lose them before you lose most of the small craters. But after that, you get a fairly similar evolution of this crater size frequency distribution to the heavily cratered terrain area. And so you can see these craters will all disappear. And that's particular to this area. You can see initially there are a lot of craters that are fairly large in this 30 to 60 kilometer diameter range, and they just get completely covered before the whole area has been filled. The last area I took a look at was the Central Highlands. This one has the smallest total relief. It's around 8.5 kilometers. And again, the same general change in elevation and volume. And when I animate this one, again, similar to the heavily cratered terrain, once you start to get the formation of plains here, you get this huge increase in volume, again, by about a factor of 35 in this case. So looking at the crater size frequency distribution, this one looks similar again to that first heavily cratered terrain area. And you'll see a similar evolution in that smaller craters begin to disappear, but unlike the other two, there's this caving in that kind of occurs, and I'll animate this to show you what I mean by that. But again, not a significant amount of crater loss until these plains start to form, and then you see a loss of small and larger craters at a faster rates than in the previous two. And again, this looks like it might be resulting from this kind of slope or orientation of this particular chosen study area, where you have the western half with a lower average topography than the eastern half. So you're losing these large craters fast, and that's how you get this loss of craters over here much sooner than you did in the very first heavily cratered terrain flooding area. Okay, so from this volume comparison, we can make a couple of conclusions about the stages of filling and add a little bit to what was done previously. So initially we have this stage one where a lot of these larger craters are being filled, and you don't see a significant change in volume or the crater size frequency distribution, just a loss of some of those smaller craters around 5 kilometers in diameter. And then the second stage really involves the formation of these inner crater plains right here, where you begin to increase in volume significantly, as shown down here in this graph, right after you reach that point, which is 3 to 4 kilometers into the flooding sequence. And then the last stage involves the formation of much thicker plains that begin to bury these larger craters. And so you can also see here that the total amount of material is relatively similar, at least on an order of magnitude basis for each of these 3 different study areas. And so we want to take kind of these studies that we've been doing and apply them to different planetary surfaces. And so in various, on the Moon, on Mercury, and on Mars, as shown over here, there are various criteria for identifying volcanic plains, and they involve these completely flooded craters that you can see in these 3 images, as well as partially buried craters where you're just seeing the top of the rim or some pre-existing terrain poking up from the volcanic plains. And you can also look at crater population differences between these volcanic plains areas and the surrounding topography. And so what we want to do with this current data set is be able to apply looking at crater size frequency distributions of various planetary surfaces with those that we've been able to come up with here, and look at to see if we can estimate thicknesses and relative ages, even looking at the map patterns to determine some sense of volume for these different deposits. And then thinking about the individual flood basalt eruption volumes for terrestrial examples, you can get a volume of around 2,000 kilometers cubed. So if you think about that as a single eruption volume, and then you consider those volumes that we calculated here for these 3 study areas, the range in the number of eruptions would be anywhere from 7,500 to 10,500 individual eruptions of this size in order to fill these specific terrains. And so some more specific applications that we'd like to investigate a little bit further include looking at Mercury, smooth intercrater plains, and possibly determining the origins of these intercrater plains, as well as trying to apply this to early resurfacing on the Moon and looking at cryptomare and seeing if we can begin to understand resurfacing histories, volumes, and maybe even relative ages of deposits. So in conclusion, we have the formation of intercrater plains where you have an initial small change in volume, and then once these plains form, all of a sudden volumes increase significantly with each flooding interval. There are 3 stages. You have the deep craters filling, the formation of these intercrater plains, and the formation of thick deposits. The crater size frequency distributions begin to experience significant loss of craters less than 30 kilometers in diameter once these intercrater plains form, and I've marked right around 30 kilometers in diameter here to give you a sense for what I'm talking about there. But then once these thicker plains begin to form, that allows for the loss of craters of all sizes in the particular study region. And so what we'd like to do with this is take this a step further and start modeling flooding from specific point sources and saying you're having an event in a specific location and seeing how that changes in different study areas. So, thank you.
Thank you. Go ahead.
So I was looking at your I guess, no, it's too late. I was going to say, looking at your simulation, it looks to me like the size distribution of the craters doesn't really change a lot until you really get a lot of flooding over a lot of terrains. So how do you define when a crater is erased? Do you have to erase every little last bit of it, or just 50%? Or
it's when the entire rim has been completely buried. So in some of those cases, at the very end of the simulations, you'll see a few craters that are still on those graphs that maybe there's just a single knob that's sticking up from the flooding. And I was trying to think of a way to quantitatively say that these craters are erased, and so like saying 50% or something like that is something I'd like to try and do in the future to maybe make it a more realistic simulation of what would happen if we were looking at a planetary surface and trying to do crater counting on those those surfaces and compare them.
Okay.
Any other questions? Okay.